NEC Article 230.91 states that transformers shall be installed and connected in accordance with the following requirements. Firstly, overcurrent protection. Secondly, primary overcurrent protection shall be provided in the primary circuit external to the transformer. The protection shall be rated or set to limit the current to not more than the primary current rating of the transformer. NEC Article 450.4 states that overcurrent protection is required. Primary overcurrent protection shall be provided in the primary circuit external to the transformer. The protection shall be rated or set to limit the current to not more than the primary current rating of the transformer. Based on the provided NEC articles, there is no specific rule that prohibits the use of a larger transformer, in this case 225 kVA, than the one specified, 150 kVA, provided that proper overcurrent protection is installed. The primary and secondary overcurrent protection devices must be rated or set to limit the current to not more than the current rating of the transformer. Conductors, clearance, and other requirements are properly sized. The conductors, clearances, and other requirements for the 150 kVA transformer must be followed for the 225 kVA transformer. Therefore, installing a 225 kVA transformer in place of the specified 150 kVA transformer does not violate any NEC rules, as long as the above conditions are met. In simpler terms, using a larger transformer than specified is acceptable under the National Electrical Code, or NEC, as long as certain conditions are met. The NEC Articles 230.91 and 450.4 focus on overcurrent protection for transformers. The primary requirement is that the overcurrent protection, such as fuses or circuit breakers, on the primary side of the transformer must be sized to protect the transformer itself. This means the overcurrent device should be rated to limit the current to no more than the transformer's primary current rating. When you use a larger transformer, like a 225 kVA transformer instead of a 150 kVA transformer, the primary overcurrent protection must still be sized according to the primary current rating of the transformer actually installed, which is the 225 kVA transformer. The NEC doesn't prohibit using a larger transformer, but it mandates that all protection and conductor sizing be appropriate for the installed transformer's capacity. This includes ensuring the conductors are adequately sized to carry the load and that clearances around the transformer meet code requirements. In summary, if the overcurrent protection on both the primary and secondary sides is correctly sized for the 225 kVA transformer, and if the conductors and clearances are also appropriate for the larger transformer, then using the 225 kVA transformer instead of the 150 kVA transformer is compliant with the NEC. The key is to ensure that all components are rated and installed in accordance with the actual transformer being used, not the originally specified one. When deciding to use a larger transformer than initially specified, several factors should be considered to ensure compliance with the National Electrical Code, NEC, and to optimize the electrical system's performance. Firstly, the primary and secondary overcurrent protection must be appropriately sized. This means that the fuses or circuit breakers protecting the transformer on both the primary and secondary sides should be rated to protect the transformer's windings from overcurrent conditions without exceeding the transformer's rated capacity. NEC Article 450.3 provides guidance on transformer overcurrent protection. Secondly, conductor sizing is critical. The conductors feeding the transformer on the primary side and those carrying power from the secondary side must be sized to handle the increased current associated with the larger 225 kVA transformer. This ensures that the conductors do not overheat, which could lead to insulation breakdown and potential fire hazards. NEC Article 310 provides tables and guidelines for determining the appropriate conductor size based on the ampacity requirements. Thirdly, consider the transformer's inrush current. Transformers draw a high inrush current when initially energized. The overcurrent protection devices must be able to withstand this inrush current without nuisance tripping. Some circuit breakers and fuses are designed with time delay characteristics to accommodate inrush currents. Fourthly, clearances and ventilation are essential for safe operation. Transformers generate heat during operation, and adequate clearance around the transformer is necessary to allow for proper ventilation and cooling. This helps prevent overheating and extends the transformer's lifespan. NEC Article 450.21 provides requirements for transformer room ventilation. Fifthly, the available fault current should be evaluated. A larger transformer can deliver a higher fault current during a short circuit condition. The electrical system's components, including the switchgear, panel boards, and conductors, must be rated to withstand the increased fault current. A short circuit study may be necessary to determine the available fault current and ensure that all equipment is adequately rated. Sixthly, consider the load calculations. The electrical load connected to the transformer should be accurately calculated to ensure that the transformer is not overloaded. Overloading of transformer can lead to overheating, reduced efficiency, and premature failure. NEC Article 220 provides guidelines for calculating electrical loads. Seventhly, the voltage regulation should be checked. A larger transformer may have different voltage regulation characteristics compared to the originally specified transformer. Voltage regulation refers to the change in voltage from no load to full load conditions. Poor voltage regulation can affect the performance of sensitive electronic equipment. Eighthly, the transformer's impedance should be considered. Transformer impedance affects the available fault current and the voltage drop under load conditions. The impedance of the 225 kVA transformer should be compatible with the electrical system to ensure proper operation. Ninthly, labeling is important. The transformer should be clearly labeled with its kVA rating, voltage ratings, and other pertinent information. This helps ensure that electricians and maintenance personnel can easily identify the transformer and understand its characteristics. Tenthly, documentation is essential. Keep records of all calculations, equipment specifications, and installation details. This documentation can be valuable for future maintenance, troubleshooting, and system upgrades. Finally, local codes and regulations should be followed. In addition to the NEC, local electrical codes and regulations may have additional requirements for transformer installations. It is important to be aware of and comply with all applicable codes and regulations. By carefully considering these factors and following the relevant NEC guidelines, you can ensure that the installation of the 225 kVA transformer is safe, reliable, and compliant with all applicable codes and standards. When replacing a 150 kVA transformer with a 225 kVA transformer, a detailed analysis of the existing electrical system is paramount. Here is a breakdown of key considerations. Firstly, overcurrent protection. The primary and secondary overcurrent protection devices, typically fuses or circuit breakers, are crucial for protecting the transformer from overloads and short circuits. The NEC mandates that these devices be sized appropriately to protect the transformer's windings. Using a 225 kVA transformer means the current ratings will be higher compared to a 150 kVA unit. The overcurrent protection must be recalculated based on the 225 kVA transformer's primary and secondary current ratings. Refer to NEC section 450.3 for specific requirements. Secondly, conductor sizing. The conductors feeding both the primary and secondary sides of the transformer must be adequately sized to handle the increased current. The ampacity of the conductors must be sufficient to carry the load without overheating. This involves considering the conductor material, insulation type, and ambient temperature. NEC Table 310.16 provides ampacity ratings for various conductors. Dating factors may also need to be applied based on the installation conditions. Thirdly, inrush current. Transformers exhibit a high inrush current when initially energized. This inrush current can be several times the normal full load current and can cause nuisance tripping of overcurrent devices. Overcurrent protection devices with time delay characteristics such as inverse time circuit breakers or dual element fuses are often used to accommodate the inrush current. The specific inrush current characteristics of the 225 kVA transformer should be considered when selecting the overcurrent protection devices. Fourthly, voltage regulation. Voltage regulation refers to the change in secondary voltage from no load to full load conditions. A larger transformer may have different voltage regulation characteristics compared to the original transformer. Poor voltage regulation can negatively impact the performance of connected equipment. The voltage regulation of the 225 kVA transformer should be evaluated to ensure it meets the requirements of the connected loads. Fifthly, impedance. Transformer impedance affects the available fault current at the secondary terminals. A lower impedance transformer will result in a higher fault current. The available fault current must be calculated to ensure that the downstream equipment, such as panel boards and circuit breakers, are adequately rated to withstand the fault current. A short circuit study may be necessary to determine the available fault current. Sixthly, clearances and ventilation. Transformers generate heat during operation and require adequate clearances for ventilation. The NEC specifies minimum clearances around transformers to prevent overheating and fire hazards. The installation location must provide sufficient ventilation to dissipate the heat generated by the 225 kVA transformer. Refer to NEC section 450.21 for ventilation requirements. Seventhly, grounding. Proper grounding is essential for electrical safety. The transformer must be grounded in accordance with NEC requirements to provide a low impedance path for fault currents. The grounding conductor must be sized appropriately to handle the available fault current. Refer to NEC Article 250 for grounding requirements. Eighthly, load calculations. The load connected to the transformer must be accurately calculated to ensure that the transformer is not overloaded. Overloading a transformer can lead to overheating, reduced efficiency, and premature failure. The load calculation should consider all connected loads, including lighting, receptacles, motors, and other equipment. Refer to NEC Article 220 for load calculation methods. Ninthly, coordination study. A coordination study may be necessary to ensure that the overcurrent protection devices are properly coordinated. Coordination ensures that the overcurrent device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. A coordination study involves analyzing the time current characteristics of the overcurrent devices to ensure proper selectivity. Tenthly, labeling and documentation. The transformer and associated equipment must be properly labeled to identify the voltage ratings, kVA rating, and other important information. Accurate documentation, including drawings, calculations, and equipment specifications, should be maintained for future reference. In Illinois, as in other jurisdictions, electrical installations must comply with the National Electrical Code, as well as any local amendments or regulations. It is crucial to consult with a qualified electrical engineer or inspector to ensure that the installation meets all applicable requirements. By thoroughly evaluating these factors and adhering to the NEC and local codes, you can safely and effectively replace the 150 kVA transformer with a 225 kVA transformer. It is important to remember that electrical work can be dangerous, and it should only be performed by qualified individuals.